I've placed a rubber onto this board. It's a rubber that's been used for experiments but never actually been used for rubbing out, so that the corners stay nice and sharp. I'm going to apply a force to this rubber using this pencil. I'm going to keep the force horizontal, so first of all I'm going to apply a force near the bottom of the rubber, and you can see that it slides. If I apply a force near the top of the rubber, it topples. And the question is to find the point on the rubber where this changes. I need to measure the width of the rubber, which is 2 centimeters. I also need to know the coefficient of friction between the rubber and the board. To find this, I've placed the rubber on the board and I'm going to lift the board and see what angle the board makes with the horizontal when the rubber begins to slide. About 37 degrees. To calculate the coefficient of friction, I'm going to use an idea called the angle of friction, which says that tan alpha is equal to mu. Alpha is the angle at which the particle or object starts to slide. So in this case, mu will be equal to tan of 37 degrees, which is 0.75. When the rubber is on the point of sliding, these are the forces that are acting: the weight, the normal reaction, the force that I was applying with the pencil, which I will call P, and the friction force. In this situation, the reaction force and the weight balance, so R will be equal to mg, and the applied force P and the friction will balance, so P will be equal to F. As the rubber is on the point of sliding, F will take its maximum value of mu R, but R is equal to mg, and mu we know is 0.75, so that will give us 0.75 mg. I'm now going to consider the case when the rubber topples. So the force diagram is very similar, but notice I've now moved R across. I should really draw it right at the corner, but it gets a bit lost because as the rubber topples, the reaction force will be acting on this point. And I'm going to call this distance X and take moments about this corner here. Notice that as R passes through this corner, it will have a 0 moment, and F acts through this corner, it will also have a 0 moment. So we will have mg, and the distance is half the width of the rubber, so that is 0.01, and that would, on the point of toppling, balance the moment caused by P, which will be P times X. So if we rearrange this to find P, we get P is equal to 0.01 mg divided by X. When the two values of P are equal, the rubber will be on the point of trying to decide whether to topple or to slide. So if we take our two values from our earlier equation, we had 0.75 mg, that's the value of P for sliding, and we've got 0.01 mg over X, that's the value of P for toppling. We can cancel out the mg's and rearrange to get X equals 0.01 divided by 0.75, which will give us 0.013 meters or 1.3 centimeters. I've drawn a line on the rubber at a height of 1.3 centimeters. So just above it topples, just below it slides, and if I push right on the line, it's sort of a mixture of wanting to slide and wanting to topple.